Hey, I'm Jessie, a decidedly non-technical person, and today I'm diving into data imputation tricks with Bill Constantine, one of our leading principal data scientists here at Xyonix. Let's get started. Today we're talking about autoencoders and imputation more generally. I did do a bit of background research into this, but I'm still probably going to be asking you pretty basic questions because, as I've stated time and time again, I am not a technical person.
So what an autoencoder is, it's a special type of neural network that's trained to replicate in its output the input that you put in. In my lifetime, I dealt with a lot of different types of data: heart rate variability data, ECG data, helicopter noise data, radar data, satellite imagery data. All of those can fundamentally have some problems with it. Can we just very briefly talk about when you have a neuron that's connected to another neuron? You usually do it visually through a line that connects the two. The strength of that connection is what's known as a weight or a parameter. You can think of it as a little volume knob. When you do training, you're basically twisting all these little volume knobs such that you get a minimal error in what you're trying to predict. And so once a model is trained, all those volume knobs are sort of set.
So I believe with my rudimentary research skills, imputation is a part of the data preprocessing phase. Is that correct?
It can be. It's not required, but you oftentimes deal with problems in the data, especially with traditional machine learning models. You would want to feed in as pristine of data as possible. So, for example, when I did work with radar data for one of our military programs, for some reason, I didn't know why, there were big dropouts in the radar data. Certainly it had to do with some sort of equipment problem, or they knocked it out because they didn't want me to see it. Who knows, right? But in order to understand the underlying statistical patterns in the data, you generally have to deal with filling in those blanks, or oftentimes you'll have noisy data as well, like things that are abundantly noisy. With the ECG data, for example, you'd have ambulatory noise, you'd have line noise, you'd have all this stuff that you wanted to clean up so that you could subsequently process the data in a way that you could pull out things that were more reasonable. Noise and missing data are things you typically have to deal with when it comes to like time series analysis stuff, for example, happens quite a bit. But Jess, in your world, I'm guessing you would encounter missing data with surveys, right? Like you'll send out surveys and you'll have people that will answer maybe only part of it, if they do respond at all, right? And then, or there might be questions that they're sensitive to that they just don't want to answer. And you're like, oh, shoot, I wish they would have answered that question, because this person is quite interesting and maybe unique in all the other answers that they had. It'd be nice to have that data point so I can understand population better.
Yeah.
You can choose also to ignore missing data if you.
True. But imputation is really only part of the data preprocessing phase, but it's only needed if you don't have the data you need. If you have all of the data you need, you wouldn't do it. That's
a great question. You know, in the world that we live in, we have a fecundity of data, maybe way too much. So if we have missing data, it's like, see you later. But for data where the dynamics that you see are somewhat unique amongst its peers, like maybe you have a certain time series that is hard to capture, so you don't have a lot of that particular type. Might be financial, might be measuring blood flow or something in the body. You want to keep that data as much as possible. So you got to try to fix the data in some way, shape, or form. And that process is officially called imputation.
Okay. And so when I have a data set with a bunch of missing data, the solutions that come to mind are either get more data or imputation. Are there any others, or is that kind of the general sphere of, oh, okay, I have a problem, I have missing data, I need to fix that?
If you can get more data, fine, that's nice. That's one way. The other way is to ignore it. If you have enough data, you can ignore it. And the other way is to try to fix it.
With imputation?
Yeah, imputation is just this concept of using model-driven ways to fill in the gaps, basically.
Okay, cool. So we want that.
So by the way, I have a little life story for you.
Oh yeah, please.
And it somewhat relates to the blog that we wrote about real estate stuff. So I used to work for a company not to be named. That company did a lot of things, but one of them was home valuations, given home facts. And during the interview process, I had to have a little take-home thing to do. And part of the problem I was given, I had data that had missing values. I chose one of the methods that we just discussed, which was ignore it, basically. Created the model and so forth. But it came up during the interview, and it's sort of the one thing is like, hey, you didn't do any imputation. I was like, yeah, I didn't have time, basically. So what would you have done, et cetera? We had the conversation from there. It does come up in real life, in real jobs. So let's say that, Jesse, I gave you sort of the same stuff that I was given. I have these home facts. The home facts, which are known as the features, could be like square footage, how many stories there are, number of bathrooms, does your house have a view, is it by the water?
Mm-hmm.
There are hundreds of different things that you could possibly have to describe a home. So let's say that you have one home that's missing lot size, okay?
Mm-hmm.
You could say, well, I have all these other homes that have lot size. I'll fill in the home that has the missing lot size with just the average of the lot size in the homes that I have that data for. And that gives you something reasonable, right? It's in the ballpark.
Mm-hmm.
How do you think that fares if the home is in a farm versus in the city? Like, do you think that average is going to be close?
Probably not.
Probably not, right? You have a beautiful view of your nice apartment there, I guess, in downtown Seattle. Right? But look behind me, right? My lot size out here in the beautiful wine country is likely to be much bigger than the typical lot size that you would see in your city, right? So a smarter thing to do would be to say, let's ask some questions of the data. Like, how about I look for properties that are out in the country? That will get me probably a lot closer, right? And then maybe I look at things like, well, I'll find properties have a similar tax assessed value, right? That's important. Bathrooms, probably not so much, right? You understand, if I ask these sort of important questions of the data, I might get a subset of the data where the subset has this value, and the average of that value, or the median, whatever, that's going to be a lot closer than the average over all the data in the training. Does that make sense to you?
It does. I also want to establish, though, like what specifically makes autoencoders special as opposed to like other methods of imputation. I just went through your article, right? So you started with why are autoencoders special? The input and the output predict the same data. And then you kind of went into an autoencoder is great at reconstructing its input, either with missing values like placeholders or using a learned approach. What makes them special and different? You said in the article, the input and output they predict are the same data. So if I can use an example that for my creative writing brain is a bit more applicable. Let's say like I have a 400-page book. I take the summary on the back of the book and then I try to reconstruct the book based only on the summary. Is that like a fair analogy?
Oh, that's an interesting analogy related to autoencoders specifically. Okay. To be very clear here for like the home valuation problem, the features that we talked about, the square footage, the lot size, number of bathrooms, all those are features in a vector, right? Feed one of those in, you feed that vector in, but what you want is for the autoencoder to replicate those values on the out side. And so there's a little bit of a twist in how the autoencoder is sort of structured. First of all, these networks are built with layers of neurons, right? And the first layer feeds into the next layer, which feeds into the next layer, and so forth, all the way until you get out the door. In the first layers, you kind of have this bottlenecking that goes on, where you sort of are forcing it down to a much smaller set of numbers until you reach this bottleneck middle portion. And you can think of that bottleneck middle portion in your relation to your whole book. It's kind of like the summary of this entire book, squeezed down and compressed into this little set of values, right?
So that would capture only like the most important essential pieces of the data?
Yeah, the idea is in that encoding portion, you're sort of squeezing down the information and forcing the model understand the important patterns in the original data. And that when you unsqueeze it and you go back up on the decoding side, that's where if it replicates the output well with the input, it basically is justification or proof that it's learned those statistical patterns that are present in the data. So for example, we talked about how if you're missing lot size, right? Like a nice variable that might be a good indicator of lot size would be tax assessed value, right? The model will basically learn that. The encoder will learn that when you feed it in.
Okay. So this process of input, bottleneck layer, output, this is the autoencoder?
Yeah, the auto part is you're having it predict its input, you know.
Okay, interesting.
It should be about the same. And when it does that well, your model is now trained and tuned. Think of it as like a nice stereo system. Everything's set a particular way. So then when it feeds in something new, those volume knobs are not going to change, but they're going to predict and use the patterns that it's learned from the original training data to form an output. And this is why they're good for things like denoising, getting rid of like anomalies, these autoencoders, because If it sees something it hasn't seen before in the regular data, if it has a really high value for one of its features, it'll predict a much lower value that it's seen normally in the data. And the difference between those two will indicate, hey, that input value that we haven't seen before is anomalous. And it'll give a much more reasonable value, maybe even like a denoised value instead.
Okay.
You understand that part? Does that make sense?
Yeah. I'm also curious, like, we don't just do this process once, right? I assume that we do it multiple times.
Yeah, you just tune the model one time, but in the process of tuning, you feed it the training data through and through and through and through. Each time you do, it's called an epoch. The number of epochs that you have to do before things are settled is not set in stone. It depends on the architecture of the neural network. It depends on the data itself, et cetera. But what you do is you monitor the error because you always know the answer, right?
Mhm.
In training, you monitor the error and you see it go down, 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 down. And when it stops, you can see where the model is essentially learned enough to where you say, okay, that's good. Yeah.
I'm curious about it. I did stumble across the term reconstruction error, so that's what I assume that is, the level of error between the original input and its reconstruction.
Yeah.
How do we use that information to adjust the model?
Like if you feed in a sample 1, 2, 3, and you expect 1, 2, 3 in the output, but it comes out 1, 2, 10. You can take the difference between each one of those components, and you can do this thing called the sum of the squares, or you can sort of come up with a single value that represents the error there.
Okay.
And you do that not just for that sample, but for all the samples in your training data, and you get a collective amount of error.
Mm-hmm.
Basically, without going into the weeds here, there's this thing called backpropagation where you figure out the derivative of the loss function that sums up all this error in some way, and you use it to tweak all the little knobs in such a way that you push the model towards making less error the next time around. That's why you sort of iteratively do better. Like initially, by the way, all these knobs are set at typically like a random value. What comes out on the other side is total crap, right? It's not good. You have a lot of error, but you adjust the knobs, the weights in between these neurons in this case, in such a way that it'll lessen the error the next time through and so forth. And so it's kind of this iterative process. Once that is complete, your model is done, those knobs are frozen. And then you use that same model for what they call inference, which is feeding in new data. You get out something you're thinking is good because it's been shown to do well in training and on the test set you use to validate that output. So
yeah, and then evidently your data is imputed. Is that correct?
yeah, let's talk about that. Let's so say we have the same problem. We have lot sizes like missing.
Mm-hmm.
A machine needs a value. You can't just say blank. It needs something. So you give it some absurd value. And what we did in our case is we gave it a value of -1.
We kind of briefly touched on it earlier, but you mentioned you use placeholders like a constant value, like you just said. How do you determine which placeholder value to use?
That's a really good question. It turns out for neural networks, it's important that you do something to the data first called normalization. So when you think about home fact data, the actual magnitude of the numbers can be huge depending on the feature. So the value of a home might be in the millions. The number of bathrooms might be 1, 2, 3, 4, 5. I mean, 5 is probably maximum, right? Mm-hmm. You have lot size might be in the thousands of square feet. So you have this whole range of scale in terms of magnitude of numbers. Remember, I talked about this thing called backpropagation where you learn to tweak all the things. Mm-hmm. It's important that one of those features doesn't dominate in terms of its absolute magnitude, right? Yeah. Like, there's no reason why something just because it has a large number should be more important than bathrooms, say, but just in general. So what you do is for every single feature, you do this normalization where you force it to go between, say, -1 and 1, okay?
Okay.
Let's say that the biggest lot in the world that you'd ever see would be like, I don't know, like 10,000 square feet. So one thing you do is divide all your lot sizes in your data for that feature divided by 10,000. That way it's forced to go between 0 and 1.
Okay.
Now this sounds kind of boring, sorry.
No, it's interesting. I was wondering because when I was doing my research, it seemed like the placeholder value was like -1 or something consistently. And I was like, why? Why would it be that?
The reason is that we do that is, first of all, we force everything to be on this sort of unit scale. -1 is not a value that the model, when it was trained, that ever saw for any of these features, right? There is no negative number of bathrooms. There is no negative lot size, right?
That makes sense.
Remember we talked about how these are good at detecting things that are anomalous?
Yeah. Yeah.
It's like, okay, I don't understand what you're doing there. I just know I was trained on this other stuff, and I'm going to use the features surrounding this anomalous thing to correct it on its output now, because it's all set and trained on normal stuff. That's why it does a good job in replacing in its output that particular feature that you said is -1 with something that's more reasonable.
Okay. So you also mentioned the encoder transforms whatever row that you're feeding it into a low dimensional embedding.
Yeah,
So I know an embedding, this is a very layman's way of putting it, is like squished data. Is that a fair way to put it?
that's right. Well, an embedding is actually just a numerical representation of something. It doesn't necessarily have to be a compressed version of it.
Oh, okay.
So one of the things is they have these things called word vectors.
Mm-hmm.
Take a word and you try to encode it, which means turn it into numbers in a way such that those numbers, in terms of their magnitudes, capture the meaning of that word. What's really cool, this is getting a little bit into the geeky weeds here. If you think about this vector of numbers, you can think of them almost like X, Y, Z would be like a three-dimensional space. It would give you 1 point, right? So if you only had 3 of those values, it would point you would go X a little bit this way, Y a little bit this way, and put Z a little bit this way. But instead of thinking of it just in 3 dimensions, just expand your mind and think, well, it's the same concept, but I have maybe 128 dimensions that I'll put in some point in space. If I label that point in space for that word, like waiter, for example, and then I look at other points that are nearby, I'll see words that are labeled with things like waitress or waiters, plural, or servidor, which is like a Spanish version of that. So what's really cool about this is you see that it captures meaning because those words are close to each other in this higher dimensional space. It means that those numbers aren't just random. They've learned about those words in the context that they've used them in. That's an embedding.
Okay.
But in our case, you can think of that compressed version of your book. It's a numerical representation. It's the compressed embedding of the original data.
So is a bottleneck layer essentially an embedding, or what's the fundamental difference between the two?
So the weights that are associated with it, you can think of as the embedding.
Whoa, okay.
So one of the experiments we tried, which wasn't that successful, was just to use that embedding itself as a means of the features. So you transform the original features into this, abstract numerical space, where you might have 32 features, call them feature 1, 2, 3, 4. But the vector itself represents the statistical structure of the original data.
Okay, cool. So if we're trying to pre-process some data, what happens if one of the rows has a lot of missing features? Is the autoencoder still able to provide a pretty reliable reconstruction, or are there limitations to that?
That's a good question. If you're theoretically missing all data, like you have nothing, no other variables in there that can help you out, right? The autoencoder really works well when it understands the relationship between features and the statistical patterns that develop from those features. If you don't have many of those features at all, it has very little evidence to try to figure things out. You need something. I wanted to tell you, because we haven't talked about it, everybody and their mother uses these LLMs, large language models nowadays. For example, the popular ChatGPT by OpenAI, et cetera. I don't know if you know this, but the reason why they work so well is because in training, they purposely remove text or portions of text. They're called subtokens out of a sentence and force the model to try to predict what it should have been. So they literally introduce missing data on purpose so that the models get really good at figuring out the surrounding sort of patterns that they need to be able to fill it in with something reasonable.
Okay.
And when you talk about these large language models having maybe billions of parameters, you can think of it as they have billions of these little volume knobs that we talk about in our smaller neural network. But they've just been tuned on the world's worth of text information that's been encoded, like we talked about word encoding. They can have sentence encoding and so forth. Missing data is the basis by which these LLMs models are trained. They purposely introduce it so that they get good at filling in the blanks.
I didn't know that. That's interesting. And then I assume they use the reconstruction error to further train it on, oh, we would rather you say this, we'd rather you say that.
That's right. There's always this correction. You can imagine with that volume data, with that volume of complexity and all the little knobs, the billions of parameters that you might have to tune it with, that takes a long time to get a good model out of that. Millions and millions of dollars, lots of electricity. Talking about, developing nuclear power plants, no kidding, to be able to use these models for training and also for inference, once the model is set in stone, et cetera. It's really interesting. They're actually introducing something on purpose in terms of missing data so that they can strengthen the model's predictability. If you give it a sentence, the boy likes to play with the answer is supposed to be dog, it'll actually come up with a number of different things like dog, trees, whatever. And there'll be a probability associated with that. Usually probability is probably really high for things like dog or football or whatever, right? But it's learned that through all of its training by having it taken out. Yeah. So
that makes sense. And then it, of course, uses the context around if that's a sentence after the boy is in the park or something.
Yeah.
Or something like that.
It doesn't just predict words, it predicts these things called subtokens, which like subwords, but it doesn't matter. Let's think of it in words. It'll predict one word first, and then now that's part of the thing, and it'll predict the next word beyond that, which is now part of the thing, and so forth. So what's really amazing is that you look at the responses of these LLMs and you think, wow, that's just in its entirety. It's really conversing with me in a way that sounds like a human. But at the very fine level, it's just predicting one word at a time in what it develops, which makes it even more fascinating.
Did you see they said GPT-5 allegedly will have 1 trillion, I think, parameters?
Maybe.
Would it make a significant difference?
From Sam Altman's words directly, they've already kind of skinned that cat. The gain in you adding more parameters so that you can understand more of the subtle nuances and all the patterns that you see in the massive amount of data that they're trying to understand. I don't know if they feel like that's necessarily the best approach. Here's why. One of the things is it kind of speaks to us as humans and babies growing up as an example. We are not given the world's worth, thank God, the world's worth of information to try to understand the world around us.
Yeah.
We have a way of taking what we know and adapting it to our environment. So the future is more models that can apply logic and reason as opposed to let's just predict the next token, right? Because there's no understanding there, really. It's just a big pattern recognizer and generator. That's it. At the core level, it's just spewing out what it's seen before, but there's no reasoning on that at all. When we sort of capture how a human being reasons in the world and use models, mathematical models more aligned to that, now we're going to start pushing ourselves towards things that can think like we do and maybe don't require so much specific understanding of every little thing on the planet to be able to survive.
Such an interesting world we're being thrust into.
For sure.
So we've filled in the blanks, patched our gaps, and made our data whole again. Big thanks to Bill for letting me pester him with questions, and if you enjoyed this video, please do not forget to like and subscribe and check out Bill's full article in the description below.